Hello everyone, this is Professor Robert Solis and welcome to this video lesson. What I want to show you how to do is to run an assembly language program inside of a C++ program. So what I did, well actually you know what, let me just go ahead and start all over again. So I will, let's see here, this is what we're going to build, but let me just go ahead and close the solution and I'm going to start all over again. So first of all I want to create a new project. And I'm going to start off with an empty project. Now, initially I typed in or selected C++ Windows Console, and since I've used this empty project, empty C++ project template over and over and over again, it appears over here. But ultimately, it's just a C++ Windows program console for the console. So I'm going to go ahead and select this template, and then I'll click Next. And in terms of the name, I'm going to say CS242. And this is going to be ASM, which is an assembly language type of program. And I'll just put part 1, but I think that other one was part 1, so I'll better put part _1. I'm going to save this. Typically, it says to save it in the repos folder. I'm not going to do that. I'm going to save this in Visual Studio 2019 in the projects folder. And then I'm going to go ahead and click Create. Give it a second, and then I'm going to create a source.cpp file. So that means I have to go to the Solution Explorer. I'm going to right-click on Source Files, add a new item, and it says Visual Studio or Visual C++. C++ file is selected. Source.cpp is going to be the default name. That's fine. I'll go ahead and click Add. Okay, so the first thing that you'll do before typing in any assembly program is you'll go ahead and type in your boilerplate code for a C++ program, which of course means IOStream, and we're going to say using namespace, std, and then we're going to say int main, open and close parens, and then we'll say return 0. All right, so that's the boilerplate stuff that we type. Now what I want to do is I have a discussion on what's called an inline assembly program, or inline assembly. I should call this a program. That's really what it is. I could also, if I wanted to, say language, right? I'm talking about the assembly language, so it's really the assembly language program. So let me just do this. I'll say assembly language program, right? But we're doing this in an inline fashion, and all that simply means is that we are going to be creating an assembly program inside of our C++ program. And the way that you do that is as follows. __ ASM with an open and close curly braces. This is an assembly language module within a C++ program. So now you can start to type the mnemonics for the assembly language for the Intel processor. Well, one of those is NOOP. NOOP stands for no operation. We'll talk about that in just a second. Another operation would be to move something into the EAX register. We talked about this in previous lessons about what the EAX register is within the Intel CPU. Now, in this case, I want to move a hexadecimal number into that EAX register. What is a hexadecimal? How do I know that this is a hexadecimal number? Well, that 0x prefix tells me that what I'm about to type is in hexadecimal format. So I'm going to type in FFFF. There's 4 of them, and I have 4 more to go. FFFF. All right. Now I'm going to move into the AL register the number 2. Now this is not in hexadecimal. This is in decimal. We'll talk about the AL register. We're going to move into the AH, A high as opposed to A low. Also the number 2. And then our next instruction is going to move into the AX register, the number 2. And then finally, we're going to move back into the EAX register, the number 2, which is all in decimal. So all of these are in decimal. This is the only one that I'm moving an actual hexadecimal number. So I'm trying to show you various ways of moving data into the various registers. Okay, so let me save my work, and then what I'm going to do is I'm going to put a break right here and stop the program so that we can investigate what this looks like and what effect it has on the registers. So I'm going to go ahead and start the program, give it a second, and then you'll see that it's stopping the program right here. All right, now I want to be able to see what the registers look like. The way that you can do that is while you are in running mode, or we are in debug mode. So notice that I can push that stop symbol right there to stop debugging. So we're debugging the program. The only way that you're going to be able to see this is when you're in debugging mode. So you tap on Debug, Windows, and go all the way to the bottom, and you'll see Registers. So if I click on Registers, this sometimes appears down here. I don't like the Registers panel down here, so what I'm going to do is I'm going to drag this. It's floating. I'm going to dock it on the right-hand side. Now, you don't have to have my same setup. It's just something that I'm used to. For years and years, having stuff over here on the right hand side. So I'm going to have the registers tab or panel right over here. And what this is doing is it's giving me the state of all of the different registers within the CPU. So the EAX register currently has this. The EBX register currently has this, and so forth and so on. All right, so this data is irrelevant because, when you turn it on, who knows what's going to be inside of that memory cell. It just happens to be that these are the values right now. We're going to be changing those in just a second. All right, so we've stopped the program here at this assembly language statement, which is basically called no op. No operation is about to occur. So when I tap on this guy over here where it says step over, notice that nothing happens to the EAX, EBX, ECX, or EDX register. Those are your data registers. But to the instruction pointer, that's what the EI, or the IP, I should say, stands for, instruction pointer. What this represents is that this instruction is located at this particular memory address, and it's saying that the instruction pointer has in fact been altered. The instruction pointer is indicating that this instruction has been executed. So watch what happens. This will change again when I step over. So now this instruction located at this memory location, well, what is the instruction located at that memory? It was no op, no operation. All right, and then we'll do it one more time, and you can see that the instruction pointer has changed. So the IP, or the instruction pointer, just simply indicates where was this instruction located. It was in that particular memory location. All right, so now we are about to put a value inside of the EAX register. So when you see this move, I know this seems kind of weird. It seems almost like non-intuitive. It makes it seem like you're going to move this into this, but it's actually from right to left. This move is saying take this content and put that into this location. So you're going to take this number, which is 0x, oh that's sorry, hexadecimal, FFFF, and you're going to put that into the EAX register. So over here, this is about to change. When I tap on this to step over, now notice what has happened. FFFF has now been placed into the EAX register. All right, so now we are about to place content into the AL register. Well, if you'll recall from previous lectures, the EAX register is really made up of the AX register, which is really made up of the AL and AH register. So you could think about this as a big umbrella. You could think about this as a smaller umbrella inside of this bigger umbrella. And then you can think of this as the lower half of this umbrella and the upper half of this umbrella. So it's like, from big, smaller, smallest. All right, let's see what happens if I put the number 2 into the AL register. Well, the AL register is really these two hexadecimal numbers right here. So notice what happens when I step over. The number 2 was placed over here. Now I know that looks like decimal 2, because I did, in fact, move a decimal over there. It just happens to be that decimal 2 is the same thing as hexadecimal 2, and that's why you see the 0 over here. The AL register, if you think of this as the EAX register, the AL register is the lower two hexadecimal numbers. The AH register is the upper if you were to take 4 hexadecimal numbers, it's the upper half of the 4 hexadecimal numbers. So I'm about to move 2 into the AH register. So now notice what happens. Now this got turned into a 0 too as a result of this instruction. Now the AX register, that's these 4 hexadecimal numbers. These 4 hexadecimal numbers are the AX register. These 2 are the AH. These 2 are the AL. But I'm about to move the number 2 into the AX register. So that means that all of this is going to be wiped out, and we'll just see the number 2. Let's see what happens when I click on Step Over, and notice what has happened, right? So moving 2 into the AX register means that I am affecting these 4 hexadecimal numbers. And then finally, I'm about to move the number 2 into the EAX register. Well, the EAX register, which you can think of as an extended AX register. So here's the AX register. An extension of that AX register is a total of 8 hexadecimal numbers. 1, 2, 3, 4, 5, 6, 7, 8. You know that that hexadecimal number represents 4 bits. 4 times 8. So what is that? That's going to be 32. So this is really 32 bits. That's what the AX register is. It's a 32-bit number represented in hexadecimal. It's 1, 2, 3, 4, 5, 6, 7, 8 hexadecimal numbers. All right, so we are about to move the number 2 into the EAX register, so that means this whole thing is about to be changed to the number 2. So notice what happens when I step over. Now the whole thing changes to the number 2. All right, so that is how this works. Now, if I were to, stop the program, and if I were to just simply run it without the stop, it's just going to simply run the program, and then it won't do anything. I mean, it already did stuff. It moved over. It just simply says press any key to continue, right? So that's why whenever I'm dealing with whenever I'm dealing with assembly language programs, sometimes I like to stop the code and see what's going on here so I can take a look at that in memory. Later on, let me go ahead and run the program. Later on, we are going to be talking about something additional in the registers panel. Let me see if I right-click and if I look for flags. There it is. Beautiful. So this shows me the flags of the CPU, of the Intel CPU. So these flags represent something. If there was some sort of an overflow that occurred, if there was a 0 operation that occurred, if the parity is equal, if the sign has changed, if there was some sort of a carry, right? So all of these represent something. Now the flag can either be on, which is represented by the 1, or the flag can be off, which is represented by the 0. So you can think about these as true or false. You know what it's like when someone drops off when you put mail into your mailbox and you put the flag up. For those of you who have a flag on your mailbox, that is communicating something to the mail carrier. All right, so the flag can be up, binary 1, or the flag can be off, binary 0. So if the parity is even, well then maybe I said equal, sorry about that before. That meant parity even as opposed to parity odd. If the parity of the number is even, then you're going to get a 1 over here. That's true. If the parity is not even, then that's going to be 0. So these only have 0 or 1 for values. They represent flags of situations that you can use during your analysis. Okay, and the way that I brought that up again is I just simply right-clicked in the registers panel, and then I clicked over here on flags. All right, so I'm going to go ahead and stop the program, and I'll remove the break. So that is how you will create assembly language programs. You will create an inline program, which is __ ASM with an open and closed curly braces. And even though this is embedded within a C++ program, this is how we are going to generate our assembly language programs. All right, so this is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.